Hello and welcome to the 2021 National Science Quiz. And before we get into it, I would like to acknowledge the traditional owners on the land on which I live and work, the Wurundjeri people of the Kulin Nation, who have been custodians of this land for thousands of years. This land always was and always will be theirs. And I pay my respects to their elders past and present, and to Aboriginal elders of other communities who may be online with us today. Welcome to them and welcome to all of you to the National Science Quiz, conducted, I believe, for the first time ever, virtually. Obviously, because we are living through a pandemic, and it's an incredible time for science, it has to be said. I know myself that currently living in lockdown, for the first time ever, I've truly understood the theory of relativity, the relationship between space and time, because I now know that the smaller the space is in which you are homeschooling, the more that time seems to stretch out infinitely during the day. So there's little things like that we're learning from. It's an incredible time for science. Without science, we wouldn't understand the virus that we're currently facing. Without science, we would not have been able to incredibly find a vaccine for it in under a year from recognising the disease. There are lessons all around us of how great science is and how important it is to our lives and how science can solve great problems in the world. And sadly, though, on the radio this morning, I heard someone say, well, if science is so good, why haven't we defeated the coronavirus yet? And the answer to that, of course, is sadly, a lot of the time, science has to be delivered by politics. And that's probably the big problem in the system. Politics is the opposite of science, in my experience. Science is the art of meeting uncertainty with evidence, whereas politics is the art of having zero evidence but absolute certainty. Science is designed to learn from its mistakes, whereas politics is designed to never admit any mistakes, therefore ensuring that nothing is ever learned. If something wasn't working, well, we're going to keep doing it harder, but under a different name with a different department. Call it border choices, climate keeper. So we are today, though, celebrating science. And we are here to show that science can solve a number of problems in the real world, to show that scientists can be set about to solve pretty much any question you want to have. And we are going to have a lot of fun along the way. So let's meet everyone on our teams today. Folks at home, folks around Australia. Team number one, we have a great team here today. First up, we have a field ecologist by training, who's now one of Australia's great science communicators. She founded and is a leader of the Science Communications teaching program at the University of Melbourne. She's on Triple R every week and writes for the CSIRO magazine Double Helix. Would you please, participants, give a big round of applause to Dr. Jen Martin.
Jen, very exciting to be here, Charlie. I'm very, very, very excited. It's National Science Week. It's the best week of the whole year.
It is indeed. So tell me, why do you love science?
Well, because it's everywhere. It's all around us constantly, from my earliest days of childhood right through to every minute of my life now. You know, every decision I make, I'm pretty confident I would make a better decision if I took into account science, which I think is partly what you might have been saying about the politicians before, Charlie, perhaps.
Yeah, I think you could argue that there aren't quite enough scientists in Parliament. I think that's for sure. Joining Jen on her team today, next up we have an astronomer, director of the Space Technology Institute at Swinburne University, lead scientist with the Royal Institution of Australia, the home of Cosmos magazine, a celebrated science communicator, and also, I will say, someone who makes a very considered decision when purchasing an affordable family SUV. Would you please welcome Alan Duffy?
Yes, that's right, Charlie. 7-year warranty. You just can't. That's a scientific choice right there. Go for the Kia.
We have a string of very dull DMs with each other about buying cars appropriate once you have a baby and need a bigger car. But it's safe to say...
I'm confused, Charlie, when I hear celebrities worried about people sliding into their DMs, it was just such a wonderful intellectual and educational experience for me when I did that to you. So I really don't know what these celebrities are complaining about.
So apart from choosing the right car for your family, why do you love science?
Oh, look, I'm going to have to reiterate Jen's great point. It is the completeness of the world and that picture that you gain, and indeed appreciation for the deeper understanding of how science influences everything in the world, and has a wonderful appreciation for the beauty. The more you learn about the world, honestly, the more amazed you will be. And I really just want to emphasize that everyone go follow your scientific dreams. And even if you've never thought you had scientific dreams while you're watching National Science Quiz, but even if you've never, do, because you will be amazed at just how beautiful the world is when you get the scientific understanding as well as being able to appreciate it.
And finally, on team number 1, we have a mathematician at the School of Mathematics at Monash University, whose research areas include geometry, topology, and combinatorics. Would you please welcome Associate Professor Norman Doe? Norman.
G'day, Charlie.
Now, Norman, I'm not going to ask you why you love science. I'm going to ask why you love maths.
Oh, well, I absolutely do. I guess a lot of people in the world want to pretend that they're adults and grow up, whereas I think I love maths because it allows me to be a child, to look at the world, the universe, patterns with a sense of wonder. Everyone can do it, and I guess some people just lean into it a little bit harder, like I have.
It's interesting you make that point. A lot of, historically, kids have been told maths is hard, or some people say, oh, I'm no good at maths. But you seem to say that it's available to anyone. You just have to approach it the right way.
Absolutely. I mean, let's not kid ourselves. Maths is hard for everyone. It's hard for me. But you just have to learn to enjoy that challenge and really sort of lean into it.
Well, we are excited to have you with us today. That is team number 1, and they are taking on an incredible team number 2. First up, we have a comedian, science communicator, and storyteller who has a background in international health, but has thrilled audiences with her science shows Parasites Lost, Days of Our Hives, and Origin of Feces. Please welcome Alanta Colley.
Hello, thank you for having me.
So apart from great puns, Alanta, why do you love science?
Well, I love science. Much like God, science is everywhere. But unlike God, science has more than one book. So I enjoy science. I think it appeals to the curiosity in all of us. And that science is constantly evolving, and we constantly find new answers to old questions. So I'm very excited. I'm here to learn today, discover all of the flaws in my own understanding of science from my esteemed colleagues, and hopefully leave this quiz a better person than I entered the quiz.
A beautiful sentiment, Alanta, although a bit too humble. If you could really try and boast a bit more when you get some questions right and really rub Team 1's nose into it, that'd be great along the way as well.
I'll do my best, Charlie.
Joining you on team number 2, we have a theoretical physicist at RMIT, leader of the Theoretical Chemical and Quantum Physics Research Group. At that institution, chief investigator of Exciton Science and Fleet, and his research areas are quantum theory, particularly related to building nanostructures. Please welcome Jared Cole.
Thanks, Charlie.
So Jared, why do you love physics?
Yeah, good question. I think physics for me is all about explaining how the world works. And I like maths and I like chemistry, but somehow physics is a bit more fundamental, but I still get to do all those other parts of science as well. And something that gets me very excited about at the moment is building technology with physics. So much of what we have on a daily basis, be it phones or lasers or telecommunications, all of these things depend on fundamental physics principles, and that is really exciting because there's an inventor aspect to being a physicist these days, which is kind of cool.
And there is a physicist somewhere at the Zoom Corporation that makes it entirely possible that we're doing this today.
Exactly.
And finally, on team number 2, we have an immunology researcher at the Peter Doherty Institute who teaches in the science communication team at the University of Melbourne. She also does science communications with the Royal Society of Victoria and also sings songs to explain science. I don't know if we'll get a tune out of her today, but please welcome Catriona Nguyen-Robertson. Welcome.
Hi. I mean, if I had the answers, I could sing about the answers of the science, but they wouldn't give them to me.
I think that would be showing off if you were able to achieve that. If you were able to answer in song, that would be on an absolutely next level today. So why are you so passionate about science, Catriona?
I think everyone sort of touched on really good points there, but I love that you don't have to know all the answers. You just constantly ask questions. Why does this work? Like, how does this happen? What does this do? And I love that science gives you, I guess, the tools to probe the universe and probe everything around you and figure things out for yourself, which is quite empowering.
It is indeed. And whilst that applies to science, it does not apply to the science quiz. Whilst you do have a list of questions today, there are most definitely answers, and I will be expecting them from all of you. I've done this a number of times before. It's one of my favorite things to do is to host this quiz. I love science. I'm passionate about it. I love having fun with scientists. But most importantly, I get put in a situation that I have all the answers and I look like I know a lot more than I actually do. So I am in a position of power today, and I'll be enjoying it for the short time that we are together. So here is how the quiz is going to run. I'm going to be asking questions of each team alternately. They will have time to confer about their answer, and then they will have to answer, and we'll see if they're right. They are all multiple choice questions. Along the way, there'll be some videos to explain the answers, which will help everyone at home, but probably help the players as well today. And today you are all playing for this. Oh yes, that is, hang on, where are we? There we go. That is our trophy. That's our science trophy for this year. And I just realized the light and the zoom. The trophy that just says science. Right, so basically I think today you win science if you win this quiz today. And the other thing I would say is there is a point for every question, but I will pretty much make up the points as we go along. If I think someone has answered very quickly, I might give them an extra point, or I might not. I might want a longer answer. If someone accidentally answers the question correctly, that might be worth a point. If someone makes me laugh, they might get an extra point today. So that's the system. There are no rules. I'm just going to ask questions. It is your job to answer them. Players, are you ready for the National Science Quiz 2021?
Yeah,
wonderful.
bring it on.
Let's get going.
We are ready.
Right, so to team number one, question number one. And this is all about lightning. Lightning is basically a huge battery discharging in a way that looks incredible. It releases enough energy to keep an average house going for a few days. The power released is measured in the gigawatt range. So my basic understanding says that's enough to power time travel if conducted in a DeLorean. Now, these strikes are definitely powerful enough to injure people and sometimes kill them. In June 2020, at least 107 people were killed by lightning on one day in India during a monsoon. On a slightly lighter note, an American park ranger called Roy Sullivan has the unfortunate Guinness record of being the human being most struck by lightning. He was struck 7 times between 1942 and 1977. Nonetheless, he persisted with being a park ranger. But it seems that golfers and footballers are particularly in danger, although you would think that swimmers are at a greater risk, which brings us to the question today. The question is, if you are a swimmer, are you most at danger in a lightning storm if you are A, if you have just been swimming in a river, B, if you have just been swimming in the sea, or C, if you are dry? So when are you in most danger from lightning? Having just been swimming in a river, the sea, or if you're dry? Team number one, talk it through.
All right.
So team, do you conduct more with salt or without salt?
Yes, definitely. I love the way you're thinking. I was thinking about that direction too. So yes, if salt water definitely conducts more easily, and that means B would conduct more than A, assuming the river is fresh water. When does it
point.
damage
Maybe it's
you,
a
though,
trick.
the storm? Well, that's what I was wondering, because you're more in trouble when the lightning strike runs through you, whereas you sort of see those classic in the lightning cages where the scientist wears a chainmail armor, so to speak, and the electricity goes through that rather than through them to hit ground. So I sort of wonder that maybe if you've just been swimming in the sea, you're going to be nicely wet and coated, and by the salt water, and it's going to go through that perhaps rather than through you. That's why.
Well, unless you were scuba diving with sharks and you had your chainmail suit on, then that would just change everything, right?
There's definitely risk profiles here, right? So yes, if you're chainmail swimming anyway, I think lightning is probably the least of your worries. Yeah.
Extra challenge.
So can I just ask you? You seem to be leaning towards salt water being more likely to conduct electricity. Can you explain why scientifically?
I can't. Over to you, Alan.
Oh, I was going to say, Norm, it's your turn. You've been amazingly quiet at this point, so I'm going to throw you into that bus.
Do you know why? Alan? It's because Norm totally knows the answer, and he just wants us to look like fools messing around with all the possibilities. Then he's just going to come in and say, "Guys, don't be ridiculous." It's
No, absolutely not. I was going to say something to do with the word ions, and then hand it over to my.
Right. Okay. I'll jump on this grenade. So basically, electricity is the flow of charge. So we think about electrons flowing in a wire, a current that essentially, because they're so light, they're able to travel more easily than the positive ions that they're stripped from. So when we talk about with electricity being conducted through salt water versus fresh, again, in this instance, it's just those ions floating around. That's the salts that are dissolved into the sea. They're charged, and they're able to essentially carry that charge more easily through them, through that body of water. Now, so this is why I was thinking that perhaps that gives you some protection. I think your chances of being hit by lightning are, roughly speaking, similar in the sense that, as the fork makes its way down from the sky, and there's a little countercharge, going up from the land. Essentially, just whatever connects first, that's what the charge will flow down. So, in other words, you're the same height regardless of having gone in the sea or just standing in dry. So essentially, there's no difference from that. You're still going to get hit. It's whether the lightning will go through something else other than you, which is why I think being wet is probably a good thing, and being wet with salt water that conducts even more of the electricity is even better. So that's why I'm going to say C, but I swear if I get this wrong, I teach physics 101 at a university. Like this is horrific if I get this wrong.
Hi to all of Alan's students. We're glad you're here.
So you're going to lock in C?
Yeah.
Sure.
Yeah, on the line.
Anyone is locked in C. The answer is B.
No!
The answer is B. You were circling the right answer so closely, and then it drifted
so close.
astray. I mean, it is about ions, and it is the fact that the salt in water dissociates, and they are the ions are charged in salt water, but they do not act as a Faraday cage. I think is the sense. The salt water itself cannot be a Faraday cage, but don't take it from me.
But also, quick question: with that wording, doesn't it look like you're out?
Oh, I thought we were outside and we were standing on the land. That's what I'm saying. You're standing at the same height. It's just whether you're dry or wet.
Okay, so this is debated, but you're wet with salt water. You've just got out. Is that that's my understanding of the situation. Short of conducting an actual experiment of you in a lightning storm, Alan, I think we have to accept just the details.
Which I'm considering now, Charlie. I feel so embarrassed at getting this wrong. Yeah.
All right, who's got the ocean in their 5K zone and who's got a river in their 5K zone? Let's go and try.
Look, the answer is B. Let's have a look why.
Here we have an empty cup. I'm now going to turn up the voltage on these two electrodes. There's no current flowing from the two electrodes. Clearly, air is not a very good conductor. I'm now going to add some pond water. I'm adding about 100 milliliters. I now turn up the voltage across the two electrodes. There's some conductance. You can see a little bit of current, maybe around 20 milliamps at 10 volts. And you can see from the LED that there's actually current flowing through this. So clearly pond water is somewhat of a conductor. I'm now going to add some salt to the pond water, maybe around 3 or 4 grams, which corresponds to the concentration of seawater. I want the salt to dissolve, so I'll mix it up. I'm now going to turn up the voltage across the 2 electrodes. Clearly, there's more current flowing than in the case of just pure pond water. In fact, you can see that the LED is much brighter. Salt water is a very good conductor, and that's because the salt breaks up into ions, and the ions can carry current. So if you're near a source of electricity, you want to have dry skin as opposed to wet skin. And if you're going to have wet skin, you should have fresh water as opposed to salt water. In an electrical storm, there's a separation of positive and negative charges between the Earth and clouds. This leads to an electric field. If that electric field is big enough, it can cause a breakdown of the air, which will allow the conduction of electricity corresponding to lightning. Now this is very dangerous because lightning corresponds to between 30 and 100,000 volts. So you don't want to go swimming during a lightning storm. Of course, whether you get electrocuted or not will depend on how well you conduct electricity. How?
So there we go. The correct answer was B. No points for Team 1 on this occasion. Alan, I do sense some resentment very early in the quiz at this stage.
I honestly think we've been robbed. I think the wording was ambiguous. I'm just, yeah, I'm going to say this is the big lie that we lost this. So I'm just putting it out there.
Okay, all right. So your point is duly noted. Now, question number 2 goes to team number 2, and this is about grass. Now, the term grass refers to a whole family of plants, including wheat, corn, sugarcane, rice, and bamboo, which seem to have a common ancestor dating back about 100 million years. And humans have even adapted them to really useful causes like cricket ovals, tennis courts, and front lawns, which in my experience tend to grow very well. But of course, that means it needs to be mowed every few weeks. And I have a question with regards to that. The question is, does your lawn grow at night? A, yes. B, no. C, yes, but only when the moon is up. So, team 2, what are you thinking?
Right.
This is biology, so I'm looking at you two.
Well, I'm wondering if it has anything to do with photosynthesis, which requires light from the sun, not moonlight. So,
Yeah, I would guess the moonlight is not strong enough for it to be any significant growth. But does photosynthesis turn on and off instantaneously? Or does it take a few hours? Does the plant continue growing after the sun stops? I don't actually know.
It's a good question. Does the chemical process continue, and generate growth even after the energy source is gone? I mean, personally, my hunch would be to lean towards yes, but it's not speaking from strong knowledge on the topic.
So at this point, we're toying with yes at this stage. Catriona and Jared, what are we thinking? Do we concur with Alanta's gut that it does just grow at night?
I can imagine that the process wouldn't be as efficient, but I don't see why it would stop altogether because, why would it necessarily just immediately cut out because the sun's gone?
So actually, there is one thing that I've just thought of. So isn't the capillary action, so the plant, when plants absorb the water from the ground, this process where it sucks water up to the leaves is also driven by the sunlight on the leaves. Maybe that capillary action stops at night, but I still kind of feel like, I mean, I know that you can't use any logic from animals with plants necessarily, but we still grow in our sleep because the process is still going on, even if we're not eating.
And if we go far back enough, I'm sure that grass and humans have a common ancestor. So that's good.
I've certainly met humans that would support that.
So, team 2, are we ready to lock in A?
I feel confident with A. How about you two?
Feel unconfident in A, but yes.
Yeah, I'm sort of like, sure.
All right, we are locking in option A.
I've seen it happen in movies.
And you are correct. It is option A. And Jared, the physicist, came closest in the explanation. It was actually a combination there of working together. It was gut, it was some photosynthesis theory, but also relating it to the idea that we grow at night. In general, plants collect energy during the daylight hours from photosynthesis and convert that energy into new growth at night. So grass actually tends to grow at night and gather the energy to grow during the day. So the gut was correct with a little bit of science along the way. That is 1 point for team number 2, and no doubt some deep resentment from team number 1. Well, team number 1, it's your chance. It's your chance to catch up right now. Question number 3 is about bicycles. My question is this: if a bicycle has identical wheels, same rims, same tyres, same air pressure, and a rotation counter is fitted to each wheel, when the bike is ridden, does A, the front counter increase more quickly, B, the back counter increase more quickly, or C, each counter increase at the same rate? What are we thinking, team number 1?
Surely seems like a trick question to me as the person with no maths or physics knowledge since high school.
Or it could be the double bluff. I'm not sure, but I guess, there's a lot of the word same in the question, which suggests that you look for the word same in the answer.
So yeah, the wheels are identical, and they each have an identical counter attached to them. Do any of you ride bikes?
Yep. But I don't know. I don't have a counter. My life is bereft. I don't have a counter on my wheels. Can I go and do an experiment? I'll be right back.
I'm not much of a rider, so I'm more of a theoretician. I'm going to go out there and say this might be A. You can imagine if you're sort of like just got your back wheel on the spot and sort of turning lots, that front wheel is going to pick up a lot of rotations compared to the back wheel. And I guess when you're generally riding, unless you're always riding in a straight line, typically every time you turn, your front wheel might just do a little bit more rotation.
Is everyone with Norman on this with option A, the front counter?
Well, I was going to just put as a counterpoint, just because I'm so successful at this. You've got your acceleration is going down on the rear wheel, and that that's where your chain is fixed. And yeah, so initially that's going to move, and maybe that might make a difference. I know it's a solid body rotation, like the two things should be in lockstep, but that just seems like a trick. So I've got no confidence left after one question, Charlie. So, but no, I think
I think we need to know how many gears there are. It's clearly a trick question.
Well, given that in this case the bicycle appears to be ridden by a frog, I'm not sure the number of gears is relevant. What I will say is there is no trick to there's no tricky bit of information. There isn't a secret. It's not the Tour de France. There isn't a secret engine or performance-enhancing drugs. It is a very simple bicycle as you would ride it.
If you were a frog.
If you were a frog with apparently an office job.
And really big feet.
Yes. So Alan lacks confidence. Norman, you seem very confident.
Yeah, I'm
sorry, Alan. I'm siding with Norm this time. It did me no good whatsoever siding with you last time.
It's absolutely fair. Yeah.
So with the confidence of Norman, we're going to lock in A.
Yeah, let's do it.
And Norman, well done. You are correct. Team 1, first point on the board.
Yes, Norm.
Absolutely true. And have any of you ridden a bicycle with a front wheel that won't turn, steering wise, where they won't steer? You
done a back wheel not turning.
But you would very quickly fall off that bike because you need to constantly make adjustments to the handlebars to remain upright. And even just those simple stabilizations increase the rotation of the front wheel to a noticeable extent. We've got a little bit of an experiment to have a look at. Let's take a look.
I'm Jack Hellerstedt. I'm a postdoc at the School of Physics and Astronomy at Monash University. We're here at a velodrome to see which wheel on the bicycle spins more as we go around the track. We have two separate odometers mounted on the front and rear wheels. Here you see the two odometers zeroed out before we do some laps on the track. That was tough. So that's a 13-meter difference from front to back in 1.9 Ks.
So there we go. Norm, 1 point. Well done. And something, as you say, Jen, we probably don't think about when we're riding a bike, just how much extra work that front wheel is doing. Okay, question number 4 goes to team number 2. And this is all about carbonated beverages. Now, as we all know, Albert Einstein invented carbonated beverages by splitting the beer atom in Tasmania in the mid-80s. That might not be entirely true. I didn't fact check this at all. But it is true that carbonated beverages are some of the most popular drinks in the world and can be found everywhere on Earth and even above the Earth. Now, astronomers aren't allowed to have soft drinks, but if they did, then because everything is weightless, the bubbles don't rise to the top of the drink, so it never goes flat. On Earth, however, of course, when you open a can, the carbon dioxide will all eventually escape. And so it does go flat. So today's question to team number 2, which weighs more, an unopened can of soft drink or an open can of flat soft drink? A, the open can, B, the unopened can, C, they weigh the same.
So that's a good one. Jared, I feel like this falls within your remit.
Yeah, I have a horrible feeling this is something I should know. It's interesting, Charlie, you make a reference to Yahoo Serious in the 80s, because that was one of my favorite movies as a kid and one of the reasons why I got interested in being a scientist. It was only much later that I realized how little actual science was in that movie. But anyway, I feel like, so the carbonated drink has gas at high pressure dissolved in it, and that's why when you open it, it fizzes, etc. And I feel like that's more gas that is escaping, and so just fundamentally there has to be more mass, because if there wasn't, the fact that gas comes out when you open it means that there must be more mass inside than after the gas has escaped. So I'm going to just say, well, I'll go with that, even though there might be a trick here, but I'm trying not to second guess myself and end up like Alan.
So you're going with the unopened can of soft drink weighs more. So that's answer B. Yeah. Is that you're thinking, Jared?
Yeah. Do we agree, Alanta and Catriona?
Yeah. Sorry, please tell me if I'm crazy.
I'm assuming the carbonated gas has some weight, even if it is lighter than the H2O in the can. So I think that's a good answer. Catriona, do you have a thought upon this?
Yeah, I thought it sounded legit because, as soon as you get that, that's all that gas that comes out, right? So surely that contributes to the mass before it's opened.
So we're unanimous. We might be unanimously wrong, but if we're going down,
but at least we're unanimous.
Yeah, we're going down as a team. That's what matters.
We're going to lock in B. You are unanimously right. It is the unopened can. Team 2, a dominant start, leading over Team 1. It is the unopened can. We've got a demonstration video. This is to do with apparently Henry's law, which says the amount of gas dissolved in a liquid is proportional to the partial pressures of the gas, at which point I run out of information. But let's have a look at a demonstration video.
Here's a can of carbonated beverage. I'm going to weigh it before it's open and then compare it after it's open. And it weighs about 404.7 grams. Now, if I open the can and put it back on the scale, you can see that it weighs less. It weighs 404.57, so almost 404.6 grams. So it's lost 100 milligrams of content, which is actually CO2. There's actually quite a bit more CO2 in a can of Coke or any can of carbonated beverage. Here I have a can that's been open for 24 hours, so that most of the CO2 has escaped from it. And you can see that it weighs substantially less, more than 2 grams less.
There we go. And the simplest, most imaginable experiment you could have to discover that, just do it. Just do it, put it on some scales, open a can, job done. Well done, science.
Have a Coke afterwards.
Just picture so much lockdown joy in that, Charlie, because just think you could have a can and you know, every day of the week or the month or, you know, however long we stay in lockdown for, you could remeasure your can. It could be thrilling.
Oh,
It's
absolutely
just a
thrilling.
science.
And then there are parents watching this right now going, does it work for gin and tonics? Let's find out. Moving on to question number 5. And this is about helicopters. Now, the idea of a helicopter has been around for thousands of years. A simple bamboo toy helicopter was popular in China nearly 2,000 years ago. But these days, they're much more complicated. And part of the complication is that they now often have a tail rotor. So my question to you today is, why do helicopters need a tail rotor? Is it A, it allows the helicopter to be tilted forward? B, it stops the helicopter from rotating in the same direction as the main rotor? Or C, it stops the helicopter from rotating in the opposite direction as the main rotor? So, team 1, which is it?
Well, B and C both seem a little bit far-fetched, given that surely we had helicopters without a rear rotor for a long time, and they didn't just go round and round in circles, right?
Well, actually, I'm going to
Did they?
say that it's definitely going to be B or C. And the
Okay.
reason I know that
Cool.
is because of Hollywood. And when you see a tail rotor go out, then the thing, it starts to spin around. I think James Bond has taught me this clearly in the past at some point. So I actually think I'm gonna go with the Hollywood answer. And I think
So how then did helicopters not do that before they had rear rotors?
So I have to say I can't picture a helicopter that's not had a rear rotor. I can't recall seeing one in action. So there was the kind of the Leonardo da Vinci style drawings of one where it was kind of just a central corkscrew, but I don't think that ever flew. I think that was sort of human powered and was never tested. I think everything else I've seen has had a tail rotor. I actually think it's a conservation of angular momentum answer now. And basically, as that main rotor begins to turn, it will spin, and in doing so, the overall object's angular momentum has increased, and essentially you would have to have the body then begin to spin back the opposite direction to essentially to conserve total angular momentum, which is why I think that's what the little rotor is doing. And it's so if I can read the answers, I think it's C, but I'll be honest with you, I was pretty confident last time I got absolutely crushed in this quiz. So, maybe take a balance view on it as a team.
I've never studied physics in my life, so goodness knows why I'm actually here this evening. And I'm clearly living in the past. I'm wishing Da Vinci was still with us, so definitely don't listen to me.
I mean, I like the fact that Alan's gut was led by James Bond movies and the physics was used to fill in the blanks. Yeah. And I think the big failing is that we've never seen James Bond have to escape from one of Da Vinci's helicopters as it caught fire off a cliff. But look, what I like is that Alan seems to have found his mojo again. He's got a bit more confidence. He's got a bit more swagger. Are you happy to lock in answer C, Alan?
I'm going to go with answer C. Yeah, I feel good.
And answer C is Correct. Alan Duffy.
Good job, Alan.
Back in the house.
You're back in our good books, Alan. We like you again. It's
Nice one.
Swagger, feels good.
We're going to see a little video to explain why. I'll be, a little disappointed if it's not James Bond, but let's have a look.
Roger, ready for takeoff. Whoa! Tail rotor, tail rotor, tail rotor. Whoa!
There we go. Correct. Answer C. Well done. And also, any kids looking at this, get into science. You get to play with remote-controlled helicopters. Come on. Why wouldn't you want to do it? Moving on now, Team 2, question number 6. And this is about shadows. Have a look at this. It's a classic image in film noir, a hero in a fedora and a grey trench coat, trudging through the dark streets under the bright street light. My question to you is this. As he goes past the lamp and keeps walking, does the head of his shadow move at the same rate as him, faster than him, or slower than him?
Ooh, good question. I've always been more focused on the stylistic aspects of the film noir genre, more sort of curious about where the man's going, what nefarious deeds he had in mind, than pacing the velocity of his shadow. But I'm sort of thinking along the lines of, I'm going back to the bicycle question. I'm sort of thinking if the top of the head of the man's shadow is like the front wheel of the bicycle, it's got more pivoting to do than the back wheel, which I'm going to say is his feet. So I'm sort of thinking that his shadow is going to go faster than him. But what do my teammates think?
I was actually thinking the opposite, because I was thinking the head is closer to the light, and so it's compared to the feet. So potentially it's staying in position more than the feet would be.
Interesting theory. I think you're going to have to...
Division here in Team 2. Jared, a lot of pressure on you.
So I feel that it's definitely the first, because if the person starts a long way away from the light, the shadow is very long. And so you've got the distance from the person to the light plus the length of their shadow to their head. And then as they walk close to the lamp, the shadow gets shorter and shorter, and then out the other side, it has to get longer and longer again. And so the total distance traveled is much longer for the head of the shadow than it is for the feet. So I think that's why it must be going faster.
That
I feel very, it's far more scientific than our answers. So I'm gonna go with, I think, B.
We are going to lock in B, and you are correct. And exactly as Jared explained, the head of the shadow just has a much further way to go because of passing past the light. Let's have a look.
This is Agent 3.14159. I have the documents. I'm going to the rendezvous point. I think someone's following me. Yes, there's a man in a hat following me. Aha! Where did he go? Oh, false alarm. He's past me now. Boy, he's moving a lot faster than I am.
The quality of the video footage here. Impressive.
I just want to say it's amazing to discover that Natalie Portman is not the only scientist actor of renown. Now we've had this example.
Well, there's a lot of things to take from that, the acting abilities of scientists notwithstanding. But above all, we learned that Team 2, you get another point correct on question 6. An unblemished record so far. Team 1, a lot of pressure to catch up. So we're going to move on to question number 7. A little bit of history here. In ancient Greece, it was seen as uncivilized to drink wine straight. So now it's just uncivilized to drink it straight from the bottle. It was seen as uncivilized to drink wine straight. So they would mix wine with water in a bowl called a crater, Krater. So my question is, we have 2 craters. They're very big things. And in one, we have 6 litres of wine. And in the other, we have 6 litres of water. We have to pour an amount from one into 2 and mix it up, and then pour the same amount from 2 back into 1 and mix it up. How many litres do we need to pour in each step so that the craters both have the same amount of water and wine mixed together? Is it A, 3 litres, B, 4.5 litres, or C, 6 litres?
Norm, my mathematical friend.
Norm on the team.
This is all yours. I'm just going to go and get a bottle of wine. I'll be right back while Norm works out the answer.
6 litres. Are you going to drink 6 litres, Jen?
Depends how long Norm takes to do the sums. If that's what I have to do to support my team, for sure.
Sorry, I got to say, I just tuned out. Can we head back?
Norm was too busy thinking about whether he was going to have red or white.
Okay. Surely it's C, unless I'm jumping to conclusions. You sort of tip all of the water into the wine. You got a 50-50 mix, and then you tip it straight back. Who's with me on team 1?
But hang on, wouldn't we then? Oh yeah, maybe. But what if the crater doesn't hold 12 litres and we spill half of it and then we're lost?
Jen, I think we better take your approach and just actually practice. How long do we have, Charlie?
Yeah.
Just hit pause. We'll be right back.
What I will say is that the craters are enormous. You've got as much space as you need to pull this off.
I feel more confident.
There's no trick to this in that way.
Although, team 1, feel free to go off and drink. We'll answer all the other questions and win by default.
Yeah, but we'll be really drunk by the end and we won't care. So
drink responsibly, kids. So
I agree.
Norm didn't have much hesitation at all there.
Yeah, no, that makes sense. If we're not going to have any spillage
sense
from our crater, that makes sense.
Okay, so we're going to lock in C, and you are correct. It is C, 6 litres. You pour all 6 litres of the wine into crater 1, from crater 1 into crater 2. Mix. Crater 1 is then empty. Crater 2 has 6 litres of wine, 6 of water, and then you pour half of the 50-50 mix, 6 litres again back, and they're equal. It seems very simple, but allow me to explain it with algebra.
When you put it like that.
Yeah, I mean,
it's very mission impossible.
It seems simple now, but I've always said that algebra is much easier to absorb with some aggressive flute soundtrack. And I think we've definitely proven that tonight. Well done to Team 1. Another point, back on track. Time now, though, for question 8. Going to team number 2. This question is about chrome on a BMX. Now, vintage collectors who restore chrome-plated items such as bicycle frames often use the technique to remove rust by dipping a crumpled piece of aluminium foil in Coca-Cola and rubbing it against the chrome until the rust slowly disappears. I did not know this. We're already learning something. So the question is, why does that work to remove the rust from the chrome? Is it A, the acid in the soft drink dissolves the rust? B, the aluminium reduces the rusting process? Or C, the aluminium is softer than chrome and acts as a mild abrasive material?
Look, it's a good question. There's no doubt about that. There's obviously several steps here. If it was purely the aluminium as a removalist of the rust, then there would be no Coca-Cola needed in this scenario. We know that Coca-Cola what does it do? Is it oxidization? Is that how it removes rust? Or the rust is oxidated and then the Coca-Cola removes that? Feel free, team, to jump in at any point.
I was just letting you go. It's fine. I have no idea here.
Yeah, that makes sense because it's the exposure to oxygen, right, over time. So it would be oxidation that you need to combat somehow.
And is there a process of elimination here that Alanta was saying that if it was just rubbing, if aluminium was just an abrasive, then the Coca-Cola is irrelevant to the situation?
But then it would be the same for A, because in A you only have the acid and not need the can.
So before we even get to chemistry, we've established that there's possibly an unnecessary ingredient if it's A or it's C. So purely by process of an elimination, B is looking good. But what you're saying there is if rust is caused by oxidization, there's something about Coca-Cola and aluminium that has an effect on that oxidization.
Yeah, there's some sort of chemistry happening between the aluminium and the Coca-Cola.
Yeah.
My gut is sort of saying C in that, like, you're rubbing it off because, I don't know, correct me if I'm wrong, but can you actually reverse rusting, or is it you're like sort of eliminating the rust?
Yeah,
is that a question? Are all chemical processes reversible, or is there if a chemical process works one way, can it not work the other way?
So I think he's getting at the point that the opposite of oxidation is reduction. So it probably is that it reduces the rust. Interestingly, playing the game rather than the question, Charlie accidentally said reduces rather than reverses when reading question answer B. And so I reckon it is B.
So if we use a bit of psychology rather than the chemistry required for the question, I like it.
This is how I've done chemistry.
I think we'll have to object, some unfair coaching from the judge and jury.
Oh, really? You think I've been too helpful in this situation?
Well, I guess we'll see if they get it right or not, won't we?
I'm sorry. I will be helpful, verging on patronising for the next question that I asked, question 1. So, team 2, do we have an answer? Do we have an answer that we want to lock in?
I'd like to go with B.
Yeah, I feel like maybe the aluminium reverses the rusting process, but only if it's activated with the Coca-Cola.
So are we saying the Coke is the catalyst, that's making
the
reaction?
That's great. Okay, so we're going to lock in. We're going to lock in B amidst significant protest from Team 1. That will be. I was going to say we'll hand that over to the judges. I'm the judge. Denied. But B is correct. Now, the explanation is even though the abrasive nature of the process helps with the cleaning a little, and the acid in the soft drink is important for the chemistry, Catriona, I think you're right, as a catalyst for what goes on here, the key here is galvanic corrosion, a redox process between the iron ions and the aluminium ions results in the iron ions reducing back to iron atoms and the aluminium oxidizing to aluminium oxide. An acidic environment supports the reaction better than using, say, just water. Some believe the aluminium oxide that is formed acts as a mild abrasive agent, which may also support the cleaning process. The thermite reaction, very popular with chemistry lectures, is effectively exactly the same chemical reaction. Also, Coke itself can remove the rust by converting it to ferric phosphate by the phosphoric acid. I kind of ran out of understanding about halfway through that. I believe a transcript will be available from the Australian Science Quiz. But answer B was absolutely correct. So well done, Team 2. Moving on to question 9. And do you know what? Team 1, any help you want from me on this question, I will give to you. Just say so on this occasion. I'm here to help with question 9. Question 9 is about travelling by plane. And to any of our younger viewers, that's something we used to be able to do. The question is, in June 2017, over 40 flights were cancelled in Phoenix, Arizona, when the temperature was forecast to hit 48 degrees Celsius. Why were the flights cancelled? Was it A, the air was too hot for the planes to be able to take off? B, the plane's air conditioning systems would overheat? Or C, the asphalt runways had started to melt? Is it A, B, or C?
My gut's totally telling me C, because it's in movies, right? The runway totally starts to melt when it gets too hot. It's the whole, Armageddon apocalypse thing, but, whether there's any truth to it or if it's completely an urban myth. But Charlie, you said any help we like. So what's the answer, mate?
Wait, no, I don't want to. I was going to say, don't use our caller friend on this one. I think.
Okay, yeah.
Have we got that in the bank for later, Charlie?
Yeah, absolutely. You get one phone an acquaintance, which is me.
Oh, that's harsh.
Phone the judge.
Well, I have to be as impartial as I can.
Fair enough. I think this is all coming down to lift. So hot air is less dense than cold air. And when you're a plane and you're pushing against that air, that's what you're doing to essentially drive yourself. You're moving forward. You're pushing the air out of the way. And in response to Newton's third law, it's pushing you back. And as long as you get the angle right of your wings going through, you'll actually be pushing yourself up off the air. So, and there's other ways to explain flight, like Bernoulli's equation, whatever. But it's basically, it's you're pushing against the air, and if you do it in the right way, it'll push you up, and that's your lift. If the air is too hot, you're not going to be able to essentially push enough of that air to give yourself the lift up, and that means you're just not going to be able to take off. And it's particularly problematic at the start of your journey because you're all loaded up with fuel. Well, I was about to say, and passengers and cargo, hopefully you've still got the same number of passengers at the end of the flight, but your fuel is making you incredibly heavy. And these planes are just on the verge of being able to take off. So finely tuned is the whole system. So I think when it clocks above a certain temperature, you're just not going to be able to get enough lift to take off. And that's why I think it's A.
Mental note, don't ever fly with Alan, because if the temperature suddenly changes and it gets too hot, he's just going to jettison passengers to reduce the weight.
Are we happy to lock in A?
Yeah.
Look, I still want to think that the asphalt just, starts melting. But as I said, I've only seen it in movies. I'm sure Alan's right.
Well, I could give you a tiny hint or a tiny bit of help then, Jen, to let you know that the runways of the airport in Arizona are made of concrete and would not melt in the heat.
I actually wonder if perhaps all runways around the world are made of concrete for this very reason. Would that be a fair thing to imagine?
Well, I mean,
Maybe?
I'm probably within a range of normalcy, I imagine so. Excluding your smaller regional grass runways that you definitely wouldn't be getting in a passenger jet for. But so are we happy to log in A?
Norm, are you happy?
Yeah, I think I buy that. I wouldn't explain it as eloquently as Alan, but I figure it's hard to swim through mist and easier to swim through water. So I'm going to go with Alan, A.
That was beautiful.
Yeah, Norm
so beautiful.
Norm concurred with poetry. Like that was almost a philosophical statement. I feel like I need to just ruminate on that. Yes, it's easier to swim through water than steam. I enjoyed that.
It's a national poetry quiz, right? I'm in the right place.
That's right. So I am going to say that you are correct. It was A, that the air was too hot for the plane to take off. And I'm giving you an extra point for the poetry. I'm ramping
Norm,
it up.
good one.
So there will be points for beauty. I've just decided. Points for beauty in the answers.
Beauty, eh?
So we have an explanation video. Let's take a look.
Lift of an airplane wing occurs when the air flowing over the top of the wing is faster than the air flowing under the wing. According to Bernoulli's principle, this means that the pressure under the wing is higher than the pressure on top of the wing. And as a result, there's lift of the wing and the airplane. Bernoulli's principle can be demonstrated using this hairdryer and this ball. Now the pressure of air depends on its density. Hot air has a lower density than cool air. And as a result, in hot air, the pressure is lower than cool air and lift is reduced.
That was a terribly efficient experiment at proving that exact point. So well done, Team 1. You are now up to 5 points. Team 2, you're on 4 points as we move on to question 10. And this question is actually about a promotional campaign from Lexus, and it's also about hoverboards. In 2015, Lexus released an ad that got skaters, car enthusiasts, and Back to the Future fans excited, featuring this hoverboard. And my question, is the Lexus hoverboard real? The possible answers are yes, it uses superconductors, B, yes, it uses powerful air jets, or C, no, it was a magic trick.
Wow. It's very fancy either way. I mean, we do know that hoverboards exist, seen them. They, from what I understand, the ones used use very powerful air jets down. So yes, they do make you lift slightly off the ground. They do ruin anything on the ground, anything you've planted recently, and just make a general mess for everyone else around you. That's a great video we've got there. I can't really see if it's sort of scattering everything around. I mean, it's obviously making some kind of ripple, but it doesn't look like it's pushing powerful jets down. What are your thoughts, Catriona, Jared?
Well, yeah, you would see it if it was pushing air down. You'd see that a lot more in the water, which you're not, right?
So we're left with, so if it's not powerful air jets, it's either a magic trick. Magic's very popular in science, from what I understand, or superconductor.
It's interesting that on the on both teams today, we don't have an illusionist or an expert on card tricks. I don't know if that's a hint or not, but
so interestingly, this continues a theme of 1980s movies that got me excited about science. And actually, astonishingly so here, one of the areas I work on is superconductors, essentially because I want a hoverboard. Unfortunately, they're a fair way away. So I think the story here, I did read about this one. I think it's a little bit of A and C. From memory, it is superconductors, but to get this to work, they had to build a track underneath or inside everywhere where you see the board go. I think that was the story, that it is doing what you think it's doing, but they could only go a very specific pathway because that's where they had laid the track so that the superconductor and the magnets could see each other. So you get this levitation effect.
So you're saying that are you saying, from my understanding, the thing that's doing what we need it to do is less about the board and more about where the board is going?
Yes, I think that was the story. So the you can kind of see the like smoke coming out the back, and I think the story here was they were using liquid nitrogen to cool, because we don't have any room temperature superconductors, but we do have these materials called cuprates, which are superconductors at, let's say, acceptable temperatures, which is liquid nitrogen or carbon dioxide or something like that. And I think the point was that they filled the board with that, and then underneath all of this path, and also in the water, there was a track of magnets that the board was actually passing along. I think that was the story, but I don't remember actually seeing any details. I just saw a discussion about it somewhere, I think.
And as we know, magnets are magic, so it could be.
Absolutely. And superconductors even more so.
Any advanced science is magic.
Yeah. So are we locking in A? Is that what are we right that you ruled out B purely by observation of how the experiment was working?
Yeah, I think we're pretty confident that yes, for the purposes of this question, we're going to go with A.
All right, we're going to lock in A, and you are correct. For another point, it is superconductors, and Jared was right. Obviously, had some research coming into this that there is an element of magic, that they did disguise the concrete, and it was magnetic fields working with superconductors to create the effect. And I think it's safe to say that we all want one. It was interesting. The board floats on air, but the skateboarders did keep landing hard on concrete whenever they came off. Science still hasn't solved that problem yet. And we do have an explanation of how this combination of superconductors and bad magic was pulled off.
Hi, I am Dr. Shemunti Bhattacharya, working as an experimental physicist in Monash University. A superconductor is this amazing material that wants to exclude all magnetic fields. As a result, if you put a superconductor on a magnetic field, or in this case a magnetic track, it appears to levitate, defying gravity. A superconductor doesn't just levitate, it actually stays at a fixed position in a magnetic field. This can be seen in this demonstration, where we place a superconductor on a magnetic Mobius strip track. If you give it a gentle push, it follows the track, even when it's going upside down.
Just got the song stuck in my head. It's flying high, defying gravity.
I was just wondering whether there'd be hoverboard events at the next Olympics. I mean, if we've had skating, bring on hoverboarding.
Yeah, I was mesmerized by that track too. That would be wild to watch. Either way, Team 2 takes the points on this occasion. Moving on though to question 11. Scores are level at this stage though. It is nothing but a ball of excitement at this stage. There's everything to lose and everything to gain with each question. So, question number 11, and this is about jelly babies. Jelly babies, of course, are small, chewy lollies in the shape of a baby, which seem to have been accidentally invented in England in 1864, when the inventor was trying to make bear-shaped lollies, but they actually came out looking more like babies. Originally, they were sold under the gruesome name Unclaimed Babies.
No.
But that name
possibly go wrong.
That's absolutely true. But that name didn't last long, and they were soon called jelly babies. They were the favourite lolly of George Harrison and Doctor Who, and ranked 6th in the most popular lolly in Britain in 2009. And I think we all remember that was a particularly hotly contested year. So my question is this: roughly how far do you have to jog to burn off the energy of one jelly baby? Is it 3 meters, 30 meters, or 300 meters? So team one,
as a runner here, I feel like I should know the answer, but I've never eaten just one jelly baby when I've been running. I've eaten more, so I've never worked it out. How many kilojoules in a jelly baby?
I mean, I think we're beyond how much I'm allowed to help you if we're asking that question.
I thought this was exactly when we were going to cash in our phone a friend, or phone an acquaintance. Yeah.
It depends. Sorry, I was going to say, it depends how fast you're running. Honestly, like the faster you run, the more energy you burn. So I need a kilometre per hour.
Okay, so I'll give you a calculation of 8 kilometres per hour.
Okay, so that's slow. That is a very pretty slow
gentle.
jog.
It's a gentle jogging pace.
Yeah. Okay. Well,
I mean,
it's
it's
pretty
just,
little,
it's
right?
Gonna be, if it's going to be one of those classic estimation kinds of problems here, right? Where I would hope that Norm could use mathematical trickery to Yes, where you basically just go, always pick, half in the logarithm between the two extreme. It ends up being something ridiculous that as motivated as that it's going to be A seems too short, C seems too long, B seems just right. But it doesn't seem right to me at all. That seems like a crazy distance for just such a tiny little treat, which is depressing.
Sorry, what seems a crazy distance?
Well, to be honest, B seems like a crazy distance, even though it's kind of the midway, and hence seems more, if you're going to randomly choose anything.
I was going to say the opposite, because I reckon 300 meters, because it's a lot of sugar in a little jelly baby. And I'm thinking about how many lollies you consume in the course of running a marathon when you're running way, way faster. And yes, you consume lots of lollies so you don't fall over, but you don't consume that many. And if you're jogging slowly, I reckon 300 meters.
I guess the question there, Norm, the mathematician, would be, if one jelly baby only propelled you 30 meters, how many jelly babies would you need to eat to run roughly 42 kilometers?
Yeah, I guess I have a couple of thoughts. I was going to use the mathematical rule that if you're in doubt, always choose C.
See, I told you, it's C.
That may be a fallback. I'm just thinking, the 3 meters just sounds a bit short. I'm thinking, if I do 200 meters in a minute, that means if I pop a jelly bean every single second, approximately, that's just keeping me going. I sort of doubt that. If I'm running along, popping one jelly bean per second, I reckon I'm going to get pretty fat pretty soon. Are you with me?
Mm-hmm. Yeah, okay. I'm absolutely with you.
30 meters would be me popping a jelly bean every 10 seconds. I sort of feel like I still might be putting on weight doing that. So I don't know. I think it's a toss-up between B and C, but if you put a gun to my head, I'm going to take C.
Yeah. I know nothing about the maths. I just know about the running.
Unfortunately, holding a gun to your head is not part of this year's quiz, but I will take your suggestion for next year because it would make for an exciting final round. So, Jen, as the experienced runner, you get the final call here.
Oh, look, I've contributed nothing to this team so far because I don't know anything about physics. So why not go out with a bang and, get it wrong for them if I lock in an answer? But based on pure experience rather than science, I would say C.
Locking in C, and C is correct for team number one, because a jelly baby has approximately 20 calories in it. And if you were an average weighted person around 70 kilometers, jogging at 8 kilometers an hour, you would burn 20 calories in about 2 to 3 minutes, which would take you about 300 meters. Let's have a look at an experiment.
Hello, everyone. Welcome to the Screaming Jelly Babies experiment. My name is Sami, and I'm from the School of Chemistry, currently studying my PhD in chemistry at Monash University. A jelly baby contains about 20 calories. Your body can burn this energy while doing exercise. A 70 kilogram person jogging at about 8 kilometers an hour would burn about 20 calories in 2 to 3 minutes. This would take them about 300 meters. The calories from the jelly baby come from metabolism or oxidation of the sugar or glucose in the jelly baby. This oxidation reaction can be described by dropping the jelly baby in molten potassium chlorate. But when you do this, the jelly babies don't like it because they let out a scream or howl.
Poor jelly
I think I speak
Poor
for everyone
jelly
when I
baby.
say that will stay with us for the rest of our lives.
Harrowing stuff.
That was a very harrowing experience. Oh, I hope they have a good mental health care program at that lab, because that is gruesome stuff. So correct though, team 1, and you get a point. The answer was C, 300 meters per jelly baby. Question 12 for team number 2 now. And let's have a look at a little photo. And the question is, how did this car sink into seemingly solid ground in New Zealand? Was it A, a sinkhole appeared as the roof of an unknown limestone cave collapsed? B, intense rainfall supersaturated the soil, rapidly turning it into mud, I guess like a quicksand situation? Or C, an earthquake shook the soil below, causing the solid ground to turn into a soup-like suspension? And I guess there's a secondary question, would your insurance cover it, whatever it is?
This looks like a horrible holiday gone wrong. And it's also played on every film I watched growing up that somehow involved quicksand. I sort of grew up thinking that quicksand was going to be a much larger threat in my life than it turned out to be. But clearly, maybe not a threat at all. What have we got in terms of observation here?
I was thinking immediately New Zealand earthquakes, like, makes sense, but it doesn't look like, when you said observation, it doesn't look like anywhere else has been affected by an earthquake.
Oh, that's very interesting.
Very hard one to explain to your insurance.
What good powers of observation, Kat? The brief is still on.
So I think you're on the right track here. So one of the big problems with the Christchurch earthquake was that there are whole suburbs in Christchurch that are actually now unlivable, essentially because of this. You get liquefaction of the ground because it's all shaken up, and it doesn't settle for decades, if not centuries. And so they've actually had to build a big park in Christchurch, which was a suburb, because they can't put buildings on it anymore because they're not structurally sound. Now, unfortunately, you've made me double guess myself. How many guesses? Second guess myself. That's it. Because clearly the house is still there, but maybe it's a localized effect. I don't know. But I feel like this is an earthquake thing.
So, Jared, were they sure that it was still safe for children to play in these parks?
That's what I was worried about. I was picturing screaming unwanted babies just sent out to play in the park, and it's not very nice.
A sinking playground.
As long as no group of children weigh the same as a four-wheel drive, I think we're going to be okay.
I don't think they have playgrounds there. I think it's a nature park.
Because I was thinking you could literally have a playground with a sand pit that is quicksand.
Yeah.
I think this discussion is why we have ethics committees now in science.
So do we feel like, Catriona, the environmental understanding of New Zealand is chock full of earthquakes, and Jared's observation, obviously the news reportage coming out of Christchurch and reference to liquefaction, are we reaching a conclusion?
Yes, it's looking very much like C, I think. I think we might be in agreement as a team on that one.
All right, we're going to lock in C, and C is correct. And Jared was correct. It is a process called liquefaction. An earthquake shook the soil below, causing the soil under the ground to turn into a soup-like suspension. The ground temporarily behaved like a fluid while it was shaking. It's very unique. It's like very specific conditions needed. It is called liquefaction, and it's similar to what happens actually when you wiggle your feet on damp sand at the beach, and you find that your feet start to sink under the sand, and you can even get stuck, much like a four-wheel drive in Christchurch. But that is 1 point for team number 2. And if you'd like to know more about liquefaction, let's take a look at this video.
Hi everyone, my name is Joe. Welcome to Geoscience Australia's Education Centre. So the car we've just seen sank into solid ground during a 6.3 magnitude earthquake in Christchurch, New Zealand in 2011. And what we've done here is we've replicated very similar conditions where the solid ground is made up of moist, sandy soils. And the phenomena is called liquefaction. So let's apply a shock and see what happens. So the ground begins to liquefy. The larger grains begin to shake and allow space for the mud and water to rise to the surface. Dense objects like cars sink and the building's foundations become unstable. Interestingly, less dense objects underground like sewage pipes can float to the surface during the shaking. Once the shaking stops, the ground solidifies again. Liquefaction usually occurs during magnitude 6 or above earthquakes. Lucky for us, we seldom experience earthquakes that big in Australia, but we are monitoring them at our National Earthquake Alert Centre here at Geoscience Australia.
Great explanation, and also a horrifying thought of a sewage pipe just making its way to the surface in an already catastrophic situation.
Yeah, cars and buildings down and sewage pipes up. That doesn't sound good.
No, and it's a nightmare for Christchurch property values. I think we can all agree. So scores are level. Heading into the final round of questions, there is a chance for glory, but there is also a chance for enormous failure and embarrassment. So team number 1, with question number 13, when you wash the dishes or have a bath, your skin gets all wrinkly. What causes this to happen? Is it A, the dead skin cells on the surface expand, so there's too much skin surface area for your finger? B, your body detects the invasive water as damage and so increases blood flow to the area? Or C, the changed electrolyte concentration squeezes the blood vessels and the flesh in your finger contracts?
My goodness, I'm sure I've read about this sometime in my dim, distant past, but I have no recollection of the answer. Back to first principles, gents. What do we think?
I'm thinking that picture is a very good example of pruny fingers. Why it actually happened, I don't know. Like, C looks pretty fancy with its electrolytes, but that answer's not really speaking to me at the moment. I would have thought something simple like A might have been it, but it makes me think, why does it affect your fingers more than, other parts of your body?
Yeah. I mean, talking about surface area, that kind of makes me think of, your fingerprints, that you've already got kind of additional surface area. If you go to a really microscopic level, you've got more surface area on your fingertips than you do on some other parts of your body. But yeah, I mean, why? I don't see why your body would detect it as damage. It sort of seems a bit of an odd explanation to me.
Do you imagine that over time the body would have learnt that a nice warm bath isn't that damaging?
Well, yeah.
So you'd
You'd
think.
have to think so.
Yeah. Alan, what are your thoughts?
I'm genuinely stumped. I mean, look, the last time I thought about the wrinkly fingers thing, I swear it was almost like an urban legend going around, right? Like it was your body's long past genetic cousin of a amphibian or some ridiculous connection into the distant past, and it was responding that way. These are all really interesting physical phenomena, and I'm trying to understand which is possibly the one I could be less embarrassed in guessing, because that's where we're at right now. Yeah.
So what's physically going on with these different scenarios then? What's actually happening? Talk us through it.
If your body's sitting in water, then the idea that some cells are soaking up more water, that does seem to make some sense. But then why on your fingertips and your toe tips?
You would think that it would be uniform if you were just absorbing all of this water into your skin. It would be wrinkly all over.
Yeah, I want to do the can experiment. I need to weigh myself pre-bath and post-bath and see, see how much weight I've put on.
Yeah, I don't know.
Then,
I
don't know.
But it's your body is, your skin is waterproof in the sense that you don't suffer osmosis across your body, your skin. I'm surprised at C if that was it. I don't think you would get. So this changed electrolyte concentration would seem to indicate that somehow the water is either going from the bath into your body, your blood vessels, or vice versa. If somehow you're in a salt bath, it's even more concentrated. I guess having said that, though, I did actually swim in the Dead Sea in Israel, and I was pruned, like crazy pruned. I've just had a flashback to that. So far
so
worse
it probably
than
is
anything
about
I've ever had.
electrolytes then.
Well, imagine that. I just gave a justification that it wasn't, and actually it might be. But it was.
I'm absolutely confident that's not the case, except for my lived experience that it is.
Yeah, that's right. That sounds like science. That sounds exactly like science.
Well, look, to be fair, as a scientist, I'm a theorist. I'm a theorist, and I hold true to my theories, independent of the experimental facts, like any good theorist. That's crazy. Yeah. So it was absolutely incredible how much more I pruned up in the Dead Sea. Now that's entirely anecdotal. That's not what you base scientific theory on, as you know, anecdote is not evidence, but I will leave that there as a confusing tidbit to my team, who've done much better than I in actually guessing results for this.
So then, Alan, the next important question is, do you have any reason to believe that you had more dead skin cells on your fingers at the time that you went swimming in the Dead Sea? That seems to be quite important.
I just had a delightful exfoliation, so no, I think I was. Three
okay, well that eradicates A then, clearly.
I don't know.
But it's just embarrassing we don't know, right? This is just really embarrassing that we don't know.
Basically, you've worked through a process of elimination that B doesn't sound realistic.
No, B sounds
being
odd.
Water is not damaged. A, due to Alan's comprehensive skin regime, you would suggest it's not a dead skin cell scenario in which
I also don't like the wording of that one. I don't really like the wording of too much skin surface area for your finger. That to me sounds like very odd wording.
So are we happy to lock in C?
What's the worst that can happen, guys? We can fail miserably and come last in the national science quiz, the event of the year. I mean, there's nothing writing on this, right?
This is all I've got going on in my life, Jan. I need this.
I mean, to be fair, you were falling behind before you put some poetry
Way to kick us when we're down. I don't know if I'm happy to lock in C, but I'll go along with the consensus.
And we'll blame it all on the Dead Sea if we're wrong, right?
Sounds like a plan.
Awesome.
So
let's do it.
We are locking in C from Team 1, and you are correct.
Thank God you've been to the Dark Sea, Alan.
I
mean, the Dark Sea, the Black Sea.
So, strangely enough, for a long time, it was thought that A was the correct answer, that dead skin absorbs the water and that you've got a lot of dead skin in particular at the end of your fingers. But now it's thought that it's related to nerve changes triggered by a change in the electrolyte concentration. And I believe that Alan's lived experience was exactly the right experiment to know this for sure. And that answer C is correct. You get a point. You are officially, for the first time today in the National Science Quiz, in the lead. So team
Can we
number
stop
1.
now? I think that's the end, isn't it right? Thanks, guys. It was a pleasure.
No.
As we speak, team 2, it is time for the final question of the science quiz. It all comes down to this. And you know what? I'm going to make it worth double points to make it interesting, okay? If you get it right, you win. If you get it wrong, you lose, all right? There's a bunch of pressure on. Norm's angry. He's shaking his head. I don't mind. I'm just trying to build some tension here.
I was going to say, Charlie, to come second in this competition, having got 100%, would be some very difficult science to explain to people.
Hey, Charlie, are there bonus points available at the end for good poetry?
I've written one. I legit have.
Okay, so we may, depending on the outcome of this question, we may have a poetry off at the end. Or maybe we'll just save that for book week. We'll see how we go. But question 14, and this is a question regarding probability and Christmas. A family of 4 is planning to get together for Christmas, presumably lockdown has gone well, vaccines have been distributed, and people are allowed to gather for Christmas. So a family of 4 is planning on getting together for Christmas and have decided to do a Kris Kringle, or Secret Santa. They will each draw names out of the hat and have to get a gift, a secret gift for the name of whoever they draw out of the hat. The question is, when they draw their names out, the probability of a successful draw when no one draws themselves is closest to A, 3/4, B, 1/3, or C, 1/15. And I get the feeling that Norm wishes that he was asked this question and not why his fingers go wrinkly in a bath at this stage.
You're right.
I will say, absolutely true, and I'm not giving any help. If Team 2 gets this wrong, it reverts to Team 1 to possibly give the correct answer. So, Team 2, what are you thinking at this stage? So they're each drawing a name out of a hat, and what we want is that no one draws it out, sees their own name, has to put it back and draw it out again. We just want a nice clean draw that everyone draws out someone else's name.
So when you pull out one name out of a hat, the first round, you've got a 25% chance of pulling out your own name. And then I don't know where we go from there. I'm having a strongly emotional response to this question. It's sort of taking me back to all the time someone's tried to explain the Monty Hall problem to me, and parts of my brain have just slowly shut down as I got more and more confused and upset by probability. So I'm just immediately going to throw this to the other people on my team.
Kat's doing the sums. Kat's writing. Are you doing the sums, Kat, or are you writing a poem?
The poem's done. That's ready.
So I'll play for time while you do maths.
No, because I was... Yeah, Alanta, you're right in that... it'd be like 3/4 of a chance of you not picking in the first round, and then it'd be like 2/3, and then a half. So like times them all together. It's like 6 out of 24, but that's a quarter, and now I'm just like, what?
So, Jared, are you feeling that is correct, calculating the probability for each round?
I don't know. Now I've got goats behind doors in my head as well.
I'm so sorry.
And Norman, how delicious is this to watch?
Oh, this is great. Keep going. Keep it up. I love doing this to my students.
There's absolutely no help with this because it is the final round. Everything rests on this.
Yeah, so I don't think it can be 3/4. It's just thinking elimination, because you're right. 3/4 is the probability of the first round that everything's fine. So then if everything was fine the first round, then the next round you've got 3 options, and the next person to pick could have been picked, already taken out at the first round, or there might be one of the 3 options. And that's the bit that I kind of need some paper and pen to work out, because you've got 3/4 of a successful round, and then you've got 2/3 of successful round, plus the probability that the person picking second was already removed the first time. And that's where my brain is hurting. So I kind of feel like maybe it is 1/15, because when you do this again and again, but
is that like so low? You sort of get to the point where, is it even worth doing Kris Kringle? It's just so difficult. If you've only got a 1/15th chance of getting a successful draw, it's just like more trouble than it's worth.
That's true. I was reading the question the wrong way around. It's a successful draw probability. Yeah, you're right.
So I feel like 1/3 is like a little bit more manageable.
Yep.
Christmassy, shall we say?
Yeah, in the spirit of Christmas.
But it might be one of those annoying things where the bits all add up and you end up still at 3/4 at the end. Maths is a pain.
Our conclusion, Charlie, is that maths is a pain, and that's what we're going with.
But is it maths is a pain and B 1/3, or maths is a pain and C 1/15?
Or 3/4. I think we're like
Norman is loving this. Look at him.
I think they've said their answer is maths is a pain. They've obviously gotten that one wrong, Charlie. We can wrap this up.
Okay, so I'm going to have to ask you to lock in an answer.
Well, if it was Norm's gun, I would say B for me. But I'm very happy to go with other people's gut.
It's a small group of people, and because, I mean, the smaller the group, the more likely you are to pull your name out, which is why you tend to do a Secret Santa situation in an office environment of at least 10 people, where the odds of pulling your own name out is lower. I would be leaning towards C, but again, my gut's just involved as opposed to any actual maths.
So, Catriona, we have two competing guts at this stage. It's going to be your decision. Jared's gut, Alanta's gut, or your own gut?
Well, my gut's going A or, well, actually, no, not really A or B. So I guess B, but don't want to get it wrong.
Okay, so what I'm going to do here, you want to lock in B?
We're a democratic team, so I think if two people have gone with B, that we go with B.
Okay, we're going to lock in B. Now, as god of the quiz and a lover of a triumphant ending, Norm, I'm going to give you a chance to come up with your answer. And please feel free to show your working.
Oh.
Is that literally saying we're wrong?
I would say my answer is that the answer is 9/24 or 3/8, which is closest to 1/3.
Okay, so how did you get to that?
There's a lot going on in my head right now. You probably don't want to see all of it, but let's say you've got 4 people. I'll call them A, B, C, D because I'm quite creative in that way. And A can't get their own, so they have to get one of the other 3. So you've got 3 sort of options there. Let's say A happens to get B. You can sort of just work out there's actually 3 ways that could have happened. So 3 ways A could have gotten B, 3 ways A could have gotten C, 3 ways A could have gotten D. That's your 9. That's your 9. There are actually 24 possibilities overall. It comes from 4 times 3 times 2 times 1, which we like to call 4 factorial. So 9 out of 24, it's 3/8. None of the above.
You are locking in B as well. So let's lock in B, and I will say, with a triumphant drawn end to the National Science Quiz, you are both correct. Different paths to get there, but both correct. It is 1/3. And it won't surprise you that Norm, I'm gonna show you a slide of the explanation to this. And Norm's categorization of the people was staggeringly accurate. It is A, B, C, and D. And what you can see here is all of the blue combinations in which people would have had a successful draw. There are 9 out of the 24 possible, as Norm said, which does come out closest to 1/3. So I'm going to give the points to both sides at this stage, Team 1 and Team 2. It is a draw. As always, science is the big winner, or maths as the case was on this occasion. So congratulations, everyone. Rounds of applause. Bravo. Thank you all very much for being a part of the National Science Quiz. Jen Martin, Jared Cole, Alan Duffy, Catriona Nguyen-Robertson, Norm Doe, and Alanta Colley. Thank you for joining us for the quiz. Thank you all for joining us at home. What a great thing to do as part of Science Week, and also on lockdown. What a wonderful way to spend your evening, tuning into this, learning a bit of science, and learning that scientists don't know everything. Sometimes they just know a process of figuring it out, and sometimes they just guess under quiz conditions. But what a great way to spend your time tonight. So thanks, parents. Thank you, kids, everyone for tuning in. And I'd also like to thank all of the sponsors who made the event successful and made it all possible for happening. You can see their logos on the screen now. They know who they are. And a huge thank you to everyone who put the National Science Quiz together. There are too many names to list off one by one, but you can see them on the screen right now. All of the scientists for the experiments, the committee that put the whole thing together, the questions committee who made it so tricky for all of our panelists, the outreach committee, the production team, and of course, all of the panelists here tonight, Alan Duffy, Jen Martin, Martin Doe, Catriona Nguyen-Robertson, Jared Cole, and Alanta Colley. What a great thing to be a part of. So to both of you, I think we'll have to do a shared custody arrangement for the National Science Quiz Trophy. Let's see, we've got 6 people, 2 months each for the coming 12 months, and we'll meet back here and recontest it again. So thank you all for joining us. Well done to everyone for putting the National Science Quiz together, and we'll see you next year. Goodbye.